A smooth, unbroken steel bead can look perfect on the outside, yet snap the moment it bears a heavy load. Internal defects weaken the core of the material, waiting for extreme stress to finally pull the joint apart. Finding these flaws requires a precise, step-by-step inspection sequence. We begin with physical cleaning to expose the metal, move to surface dimensional gauging to verify the profile, and finish with internal radiography to look straight through the steel. Throughout this process, we rely on the AWS D1.1 structural welding code. This provides the definitive mathematical benchmark for deciding whether a weld is accepted or rejected. This sequence aligns the physical work with established safety margins. By following these steps, the inspector ensures the joint meets the precise engineering requirements intended to withstand years of service. Step 1 is clearing away the slag left by the flux coating. You must select your removal tool based strictly on the geometry of the joint you are inspecting. For flat or convex beads with easy access, manual chipping and wire brushing are sufficient. However, if you are working with narrow V-butt joints, slag easily becomes trapped in the tight crevices, requiring you to grind the surface to ensure complete removal. Once the weld is clean, we check its physical profile using a fillet weld gauge. When placed against the joint, the gauge must sit completely flush against the base metals without rocking, which verifies the leg size and the contour of the bead. The AWS D1.1 code does provide an undersize allowance. A weld can be slightly smaller than specified. For example, a weld with a 1/4 inch nominal size can be undersized by up to 3/32 of an inch. This diagram illustrates how that rule is applied in practice. While slight underruns are permitted, those undersized portions are strictly capped and cannot exceed 10% of the total weld length. Removing the slag and verifying the profile geometry are mandatory early steps. The external dimensions are responsible for distributing the physical load across the joint. If the surface profile fails here, evaluating the internal quality becomes entirely irrelevant. Next, we hunt for surface anomalies by shining a parallel light source across the joint, and using a 5x magnifier, you can spot microscopic defects hiding along the weld toes. One of the most common issues is undercut, a groove melted into the base metal. For materials under 1 inch thick, the maximum allowable depth for an undercut is 1/32 of an inch. Under cyclic loading, the allowable undercut limit shrinks to 0.01 inches to prevent fatigue failure. Shifting top-down to measure piping porosity, the sum of visible pores over 1/32 of an inch cannot exceed 3/8 of an inch per linear inch. Strictly measuring these anomalies prevents the creation of microscopic notches along the surface. Left unmeasured, those notches artificially amplify localized stress. After confirming the surface profile is sound, we transition to internal inspection. Placing radiographic testing negatives, or X-rays, on a light box allows us to uncover hidden flaws deep within the joint. We look for specific visual signatures. Trapped slag appears on an X-ray as dark, irregular density lines running parallel to the edge of the weld, often referred to as wagon tracks. These 3 radiographic negatives side by side show the distinct differences. Slag shows up as those irregular, jagged lines. Perfectly straight dark lines indicate a lack of fusion, and rounded, distinct dark clusters reveal internal porosity. To evaluate the joint against the code, the inspector measures the accumulated length of these internal slag inclusions. If the total length exceeds the mandatory threshold, the weld is rejected. Radiographic analysis exposes the internal failure points that surface testing misses entirely. It verifies that the solid core of the joint meets the required engineering load capacity. While measuring the length of an internal defect is required by code, the true impact on a weld's fatigue life is dictated by the inclusion's specific size, shape, and position. In this extreme close-up of a material under cyclic tension, watch how a sharp, jagged slag inclusion behaves. Notice how it acts as a severe stress concentrator within the solid metal, forcing a microcrack to spiderweb outward. Under repeated stress, cracks reliably initiate at these internal notches. Just propagating that crack from the inclusion up to the surface consumes roughly 55% of the weld's total fatigue life. Identifying these issues early relies on a complete sequence: targeted physical cleaning, precision dimensional gauging, and thorough radiographic evaluation. Strict adherence to AWS D1.1 standards validates the joint against known failure points. It is the final check that ensures the steel is as strong as the blueprints demand.